Welcome to This Explainer. I am absolutely thrilled to have you here today because we are going to look at something truly mind-bending. Have you ever encountered a piece of information that seems completely disconnected from reality but is perfectly mathematically true? Well, today we're exploring a physical scenario, a really simple thought experiment involving just some sliding blocks that somehow, against all intuition, yields an impossible mathematical result.
To set the stage here, I want to share a quote from our source material today, the brilliant channel 3 Blue 1 Brown. It says, "This has got to be one of the wildest facts I've ever seen." And let me tell you, I completely agree. We're about to look at a discovery that bridges the gap between basic physics and literally one of the most famous numbers in the entire universe. And the crazy part? It all starts with a remarkably simple premise.
Section 1. The setup and the rules.
Okay, let's dive right in. To build our thought experiment, I want you to picture a completely flat surface. On this surface, we've got two blocks that can slide around. And just to the left of these blocks, we have a sturdy, immovable wall. So that's the physical space we're working in. But to make the math perfectly clean, we've got to operate in a pure, perfect mathematical environment. First up, the sliding plane is completely frictionless. Second, any collision that happens here is perfectly elastic. Third, that wall on the left, entirely immovable. And fourth, as a result of all this, absolutely no energy is lost to heat or sound or deformation. Every single ounce of momentum is perfectly preserved and transferred.
Section 2, Phase 1, the base case.
With our perfectly idealized world constructed, let's actually set our blocks in motion. We're going to start with the absolute simplest setup possible, just to see exactly how these blocks interact with each other and with that immovable wall. Imagine our two blocks. They are identical in mass. The first block is exactly 1 kilogram, and the second block is also exactly 1 kilogram. We take that first 1 kilo block and we slide it toward the second 1 kilo block, which is just sitting there between the first block and the immovable wall. Now, when the first block hits the second, because they're the exact same mass and the collision is perfectly elastic, it transfers all of its momentum to the second block. The first block stops dead, the second block shoots off, hits the immovable wall, bounces off, comes back, and hits the first block again. Under these exact, perfectly ideal conditions, if you count every single impact, so the blocks hitting each other and the block hitting the wall, there are exactly 3 total collisions. After that third impact, the blocks just drift away from the wall forever, never to touch again. 3 collisions. Simple enough, right?
Section 3, Phase 2, increasing the mass. Now, the true magic of this thought experiment begins when we escalate the variables. We're going to change the conditions specifically by making that very first block significantly heavier. Instead of a 1 kilo block, our first block is now a much larger 100 kilogram mass. The second block, it remains a tiny 1 kilo mass. We slide the 100 kilo block toward the 1 kilo block. Because the first block is so much more massive, when it hits the smaller block, it doesn't just stop. It retains way more of its forward momentum. It just keeps plowing forward, forcing that smaller, lighter block to act like a frantic pinball, taking many, many more bounces between the heavy block and the immovable wall before the heavy block's momentum is finally reversed and it gets turned around completely.
So, how many impacts occur before the blocks drift away this time? Exactly 31 collisions. Just let that number sit in your mind for a second. We went from identical masses yielding 3 collisions to a block 100 times heavier yielding 31 collisions.
Section 4, Phase 3, the giant block escalation.
Let's push this thought experiment to a massive extreme. We want to see if a distinct pattern is emerging from this data, so we need to drastically scale up the mass of that first block one more time. We are now dealing with a 10,000 kilogram block sliding toward our tiny 1 kilo block. Just think about the sheer scale of that. That 10,000 kilo block is an absolute juggernaut. When it makes contact, the 1 kilo block is trapped in this rapid-fire sequence of bouncing back and forth, ricocheting between the unstoppable heavy block and the immovable wall at incredible speeds. The heavy block just keeps creeping forward, absorbing these tiny impacts, until finally its momentum is reversed.
If you work it out exactly, counting every single microscopic bounce under our idealized rules, the total number of collisions is exactly 314.
Section 5, the grand reveal.
Okay, 3, 31, 314. By now, if you're a numbers fan, your brain is probably starting to recognize a sequence. Let's shift our focus from the individual physical collisions of these blocks to the undeniable mathematical pattern that has emerged from our data. Just walk through this with me.
When the mass of the large block was 1 kilo, the total collisions were 3. When we bumped the mass to 100 kilos, total collisions were 31. When we increased the mass to 10,000 kilos, the total collisions were 314.
So here is the absolute knockout of a realization. As you continually increase the mass of that big block by powers of 100, going from 1 to 100 to 10,000 and so on, the digits in the total number of collisions will always match the starting digits of pi. 3, 3.1, 3.14. If you made it 1,000,000 kilograms, it will be 3,141 collisions. The digits of the collision count perfectly align with the digits of pi. I mean, there's no way, right?
Which brings us to the ultimate mystery. Pi is a geometric constant. It's literally the ratio of a circle's circumference to its diameter. So why on earth does a geometric constant govern the physics of straight-line bouncing blocks on a frictionless plane? What hidden connections of the universe are at play here? It's questions exactly like these that make learning so absolutely fascinating. Thank you so much for exploring this incredible mathematical puzzle with me today, and hey, keep questioning the patterns around you.